Good afternoon. This is David Eastwood, Geotech Engineering and Testing. How you doing? I hope everybody can hear me. Let's see. Today we got an interesting project that we worked on. Geoforensic study of storage dome collapse project in Louisiana, and it's a really interesting project that I worked on. See if we can move. We got about 200 people RSVP'd on this program, and lots of civil engineers, structural engineers, industrial, petrochemical engineers, and a lot of people from various cities throughout Texas that are listening to this. If you need to reach me, my name is David Eastwood. My email is de@geotecheng.com. My phone number is 713-699-4000. This presentation and other ones, there's like 20 other ones. They're on YouTube. So if you go to Geotech Engineering and Testing YouTube channel, you're going to see a bunch of good stuff, and then you can watch them, send an email to us that you watched that presentation, and you get a CEU for it. So it's an easy thing, you can do it anytime you want. Geotech Engineering and Testing, we're located in Houston, and we've been around for like 35, 36 years. We do geotechnical, environmental materials, and geoforensic engineering. We've got a staff of 60 engineers, geologists, technicians, and support staff. We work all over Texas, Louisiana, Oklahoma, New Mexico. And one thing about us, we have our own rigs, so we can mobilize on your projects quickly. And so if you have questions, please type your questions in the Q&A section, and I answer them as I'm going through the presentation. This is the project site out there in Louisiana, north bank of the Mississippi River. And the project, this is a steel plant for like $750 million, something like that. It's a nice place. These are the domes that they keep the, basically, these are storage domes. These domes basically are 248 feet in diameter, and they store iron ore in them. They're about 124 feet high, and the capacity on them is about 200 metric tons. I mean, the thing is huge. You can't tell from this picture, but I've been there, and these things are big. The basic components of the construction for these things is, you got that 248-foot diameter structure, about 124 feet tall. This is a ring beam. This is the shell. This is the tunnel. And this is the stacking tube. So they got the iron ore in here. They store it, goes through the stacking tube. They send it in through into the tunnel, and they got hoppers. And basically, they can take stuff in and out of the storage area. Each dome is comprised of 5 structures: shell, ring beam, the slab, lean concrete foundation, stacking tube, and underground tunnel. So this is the shell, underground tunnel, stacking tube, slab. The shell dome was made out of reinforced concrete with thickness varying from 18-inch at the bottom to 10-inch near the upper vertical portion, increasing 13 inches close to the apex. The shell was connected to the ring beam. Now, this is a ring beam. It's about 3 foot by 3 foot ring beam sitting on a big chunk of concrete here. So everything's massive here. Design and construction of the domes. The underground tunnel was used to discharge the store's iron ore and ran east to west under the dome. The underground portion of the tunnel consists of each sections. They were cast in place invert section. Cast in place slab invert section. The slab was actually cast in place. The tunnel structure itself was precast. The tunnel ran under the slab of the dome and the plinth of the staking tube. And the following the cambered shape of the slab, great opening in the slab over the tunnel allowed the iron ore to pass through hoppers to the tunnel conveyor. So everything dumped to the tunnel conveyor, and they took it in and out. They took it out. The okay, we got a question here. It says the slide indicates the ring beam lean concrete. Was unenforced concrete used ring beam? Yeah, what they used was basically unreinforced lean concrete to put that 3 foot by 3 foot ring beam on it. The internal reinforcing slab was 12 inches. The slab was cambered and based on drawing was isolated from the ring beams with 1.5 inch thick non-extruding premold compression material. So there was an isolation joint between the 12-inch concrete slab and the ring beam. The ring beam itself was 3 foot by 3 foot in thickness. It was reinforced, which actually convinced the weight of the dome and shell structure. The soil solution, that's a lean concrete type deal, is 39 feet wide, 12 foot thick, which was made out of the sand, concrete, and aggregate, which is basically lean concrete. The floating slab of the dome was supported directly on top of the soil. It was 12 inches slab, supported on sand, and the staking tube rested over the crest of the tunnel. The tunnel was directly supported on native soils on a slab. It was a slab underneath the tunnel, and they put the precast tunnel arches in there. So it's on September 25th, 2013, the dome fails. That was a massive thing. There was an airplane flying by, so they took a bunch of pictures. You can see the pictures of the dome failing. Yeah, it's the tunnel going in there, and you can see all the cracks in the tunnel right there. And here's the walls, the shell walls. Here's iron ore. The whole side of the west side of the building, the dome bulged up. The soil came out of the ground. It all bulged up. See all these tunnels from each one of them? So a bunch of soil came out of the tunnel, just coughed up a bunch of soil, and you see the crack over here in the tunnel. See the big crack separation? Soil bulged up. See, the whole soil came up. Soil coming out of the tunnel here. Here's the failure. That's the stacking tube. It just cracked to pieces. You can see the stacking tube. Here's a good picture of how everything just bulged up on one side, just a bearing capacity failure. It was a simple failure cause. It was a bearing capacity failure. And that's the stack tube. The whole tunnel got separated. You can see the crack in here. This is the conveyor that iron ore comes through it, and the conveyor takes it to the plant. Crack, the conveyor. See, you just crushed the whole steel and the concrete. This is the tunnel. These are precast arches that they put in here. Project timeline, when they start construction, initial geotechnical report was done in 2011. Construction started in September of 2011. By the way, this is the lean concrete type underneath the ring beam. They call it soil solution. It's 39 feet by 12 foot. You can see the construction of the lean concrete. This is the floor slab for the tunnel. And you can see the ring beam here. This is the ring beam. This is the soil underneath the dome. They compacted the subgrade. Here's the precast tunnel sections. This is a 3 foot by 3 foot ring beam. This is a soil solution. So they got the material in there and they start putting air into it and start airing it up. Then they go in there and put steel in it and shotcrete it to build the dome. So I starts looking. This is the stack construction, June of 2012. And you can see June 2012, July, that's what the stacking tube looked like. This is the inside of the dome structure. Here's the kind of completed dome structure. Looks pretty nice. Here's another view, all three of them. These are the tunnels. This is the one that got busted. This is the inside during the floor slab construction. They compacted the sand in here. They start pouring 12-inch concrete slab in here. Here's the dome again. In terms of timeline, July 2013, they start filling this thing with iron ore. Iron ore weighs about 137 pounds per cubic foot. So it's heavy. And so then in July 30th, they start cracking in tunnel underneath the floor slab. That was a 1/4 of an inch crack in the tunnel. July 31st of 2013, Dome 1 end filling 77,000 metric tons. Crack growth in tunnel number 1 floor slab, specialty in the area below the stacking tube. The stacking tube, that was heavy, and it was sitting on top of the precast tunnel, and there was a 1/4 of an inch crack there. In 2013, on September 23rd of 2013, they're starting filling these dome again with the second shipment. In the afternoon, tunnel increased the crack to 2 inches and at 100 metric tons of filling. On 23rd, tunnel 1 substantially cracked to about 8 inches. So they stopped filling at 125,000 metric tons. That was 62.5% of the design load when they had 8 inches of crack in the tunnel. The night of September 23, tunnel 1 invert separation about 9 inches. On the 24th, the failure of the precast section of the stacking tube. At 9 a.m., roughly on September 25, 2013, falling of tunnel sections below the stacking tube. Failing of them. Pulling away from the west entryway about 4 inches. Cracking of the ring beam observed on the west side and cracking of a soil solution observed on the west side. At about 2 p.m. on September 25, 2013, the whole tunnel sections observed below the stacking tube start failing. Soil failure below the dome towards the southwest. It heaved up the soil about 20 feet. Collapse of Dome 1 displacement of about 10 feet. And the stacking tube basically sank about 50 feet. And iron ore kind of just starts flowing. So that's kind of the timeline of what's going on. Dome was collapsed on afternoon of September 25, 2013. So we were contacted. We start doing reviewing the documents. We look at the site geology. We look at the initial geotechnical investigation report. We and others look at the design of the dome, construction. materials used in construction, what kind of environmental conditions in terms of drainage they have around the domes. We did full field investigations, soil testing, elevation, excavation of test pits, laboratory testing. Here's the site. This is Mississippi River. And he said the steel plant is located on the north bank of the Mississippi River, approximately 60 miles northeast of New Orleans. The geology of the area characterized by a thick deposit of soft deltatic soil. When you look at the geology of the area, they call it back swamps deposits. Back swamps. And that was it. And when you go over there, you see a bunch of gumbo clay, soft clay. Lots of times this Mississippi River has flooded and deposited soft soils and organics here. So it had very soft soils in here. Initially, when they did the soil test for the site, they did 7 borings for these domes. 1 at dome 2, 3 at dome 1, at dome 3, and 3 at dome number 1. When they did the soil test, which they didn't do a good job, from 0 to 58 feet, they found clay. Now, they said there was organic debris in it. So there was an organic layer on this site. From 58 to 63 feet, they found silt. From 63 to 69, lean clay. From 69 to 158, fat clay. From 158 to 178, silt again. And they found silty sand from 178 to 200 feet. That's dense material. That's a really good material to put piling in. At 200 feet, which is not economical to go that deep. But anyway, that's what they found. In terms of water content and soil data, these soils were soft. They have moisture contents of about 40%. Low density in the organic layer, which was between 5 and 35 feet. This is the organic layer. That they had a lot of roots and organics deposited there. Real soft soil. They hardly ran any tests on the strength, the initial geotechnical report, which was bad. They should have run a bunch of tests. But they had organic soils between 15 feet and 35 feet. These organic soils are soft and compressible. So we have a 248-foot wide diameter structure, 124 feet tall, shell, the slab, ring beam, and tunnel. The shell was 10 to 18 inches thick. The slab was 12 inches thick. The ring foundation was lean concrete. We had the stacking tube and underground tunnel. Here's the stacking beam. This is the tunnel. These are precast arches. They backfilled with sand around it and compacted it. This is what we call the soil solution, which is a lean clay. This is sand underneath the 12-inch slab. Initial project specifications called for a bearing capacity of 1,500 PSF, which is a joke. Right off the bat, if you got a 1,500 PSF bearing capacity, you cannot load up these stacks 128 feet tall. So they said that 1,500 PSF allowable bearing pressure. So they went in there and built this thing with a soil solution, 3 foot by 3 foot ring beam. This is the sand underneath the 12-inch slab, and they had natural soils underneath the floor slabs. What they did to analyze this thing, which is a wrong model, they used final elements, and they used what's called strain hardening model. And these are the soil parameters they use: phi angle, C angle, E50, E odometer, and E rebound. And so that's the kind of a parameters they used for design. They used the unit weight of 137 pounds per cubic foot for iron ore, 120 for soil. These are the dome. Then start loading it. Soil hardening model is an advanced model for simulation of the soil behavior. We use most of the time on our projects what we call a Moore-Coulomb model. The limiting states of stress that are described by means of friction angle and cohesion. However, soil stiffness is described more accurately using three different input stiffnesses. E50, that's a modulus of elasticity at 50% strain. Traxal unloading stiffness, EUR, and odometer loading stiffness, which is EODED, in contrast to Moore-Coulomb model. The hardening of the soil model can account for stress dependency of the stiffness moduli. This means that the stiffness increases with the pressure. What they're trying to say is, once you load that structure, the soil, as you load it, it gets stronger. But their model was wrong. These are the parameters that are used in the final elements. C, cohesion, Phi, angle of internal friction, E50, that's a second stiffness in the standard drain triaxial test. E, odometer, that's the modulus of elasticity, tangent stiffness for primary odometer loading. EUR is unloading and reloading stiffness from triaxial test. M is a power, stress level dependency, stiffness, and the Poisson ratio. Here's loading one of the domes, for example, and calculating settlement. We say if you load that dome, you're going to have 1.7 inches, 1.7 feet of settlement at the center, and at the edges you have 1 foot with a differential of about 0.7 feet. Yeah, we got a question here. Somebody says they can't hear me. Can everybody hear me, or is there a problem? I didn't know there was a problem with it. So I don't know I hope everybody can hear me. When you get the three domes and you load them up and run a final element, that's the kind of a settlements you get. That's 4 foot of settlement in here. The edges are about 2 foot with the differential about 2 foot of settlement. Most people say they can't hear me. So, I mean, if you can't hear me, you got your own equipment problem. So you can see differential movements over here about 2 feet, from 4 feet to 2 feet. Here is, about 3.2, 3.0. The differential here is about 1 foot. They ran the final element and they said we have a factor of safety about 2.56 against bearing capacity, which is totally wrong. Elevation survey after the failure, it shows all the whole thing coming out, all the soil all just stacked up over here. Yeah, there's a question here. Are these results from original design calculations or your calculations? No, these are from the original design calculations. And here is the soil that's coming out from underneath the tank, just stacked up. These are elevations for it. This is the tunnel. Soil investigation after the collapse of dome. Here's the dome after I removed the iron ore and stuff. We went in there and did borings here and do CPT cone penetrometer testing. Here's far away, CPT 15 and CPT 8. Soil testing boring R5. But we did a bunch of borings here. Here's the cone penetrometer testing. This is the sleeve. This is the tip. You push it hydraulically into the soil. This is the tip. This is the sleeve. Here's a cone that you jack it up against the truck and just push it in. You can see it right there. Here's another CPT device. You can see the CPT right there, pushing it into the soil. Right there. This is inside device. You hydraulically push the tube in here. These are the tubes. So you got your basically the truck. You just hydraulic jacks lift it up, and then just push the CPT into the soil. This is the tip. This is the basically sleeve friction. It's about 1.4 inches in diameter and can go about 60 to 100 foot deep. Tip, sleeve. That's the tip, sleeve. That's the sleeve. You get a bunch of wiggly line. That's the friction on the sleeve. That's the tip resistance. That's the conductivity. Pore pressure is, as you go deeper, pore pressure gets bigger. This is the ratio of the sleeve to the tip, and this is soil stratigraphy. So what you do is you go to this table here. You got the friction ratio, which is the sleeve to the tip, and that's the tip resistance. Most of the soil on this site fell in area 3 and 2. 3 is clay and 2 is organic soils. So the good thing about CPT is it's a continuous soil sampling, identifies thin seams and layers, estimation of the geotechnical and hydrological properties, fast, no drill cuttings, and works in bad weather. We also did our standard drilling and sampling. And you can see they use the buggy rig. Do Shelby tube sampling, lots of clay, soft clay, organic clays, put them in containers to them to the lab, take them to the lab. Also, test pit excavations were conducted. TP4, TP3, T2, and T1. These are test pits. We saw a bunch of clays out there in test pits. This is the test pit number 1. You dig it out, you see all the clay out there just showing up, the whole thing coming out of the ground, just mounding on the west side of this thing. This is the shear plains. Test pit number 2. You can see them like this, the shear plains. Test pit number 3. Test pit number 2. You can see the clay soils, just gumbo clay. This is the ring beam, actually the soil solution, the lean concrete that's just cracked up. This is a test pit number 3. You see all the soil coming out, all cracked up there. Test pit number 3, see the scarp, slab movement. Lots of crack in the soil. That's a slag fill. That's the iron ore slag. And here's test pit number 4. We just found lots of organic soils. These are really soft soils with high moisture content. We also got samples of the ring beam, cored the concrete of the ring beam. That's what it looks like, concrete. Laboratory testing, we did the soil testing on the soils, concrete compressive strengths, steel tensile strengths, and petrographic analysis of the concrete and the gunite. The compression test on the concrete showed 7,000 PSI concrete. So the concrete string passed. 7,600. The steel was checked for tensile strength. Numbers was 104 KSI, 96 KSI, 104 KSI. Everything passed for the steel. We also did what's called petrographic analysis of the concrete and the gunite. So we take the cores of the soil ring, soil slab near the stack tube, vertical of the shotcrete and horizontal of the shotcrete. On the dome itself, it was shotcrete. Took these cores, took a slice of them, put them on the microscope. Again, this is the core shotcrete or horizontal shotcrete. Soil ring, got a slice of it. Core near the stacking tube. Core vertical of shotcrete. Core horizontal of the shotcrete. You put them out there and basically put an ultraviolet light on them in a microscope. And this is what they look like. And you can see the cracks, micro cracks through the polished of core F.ASCE, fluorescent dyed epoxy present within the crack. There's a crack in here in the shotcrete, micro crack. So anyway, the concrete and the soil, concrete and the steel were all okay. Collect samples of concrete and steel from the share ring beam, dome slab, and soil solution. Independent lab did the testing, tensile and compression testing. In accordance to ASTM standard, the test results among the selected samples show compliance with project specifications. Here's the crazy stuff right here. When we look at the soil data from the borings that was done, here's the organic soil layer from 15 to 35 feet. We have moisture contents is about 200%. These soils were extremely soft with 0.25 to 2.5 KSF strengths. Very soft in this layer. They should have never put a mat foundation on top of these soft soils because the differential settlements are significant. The densities were light. I mean, 50 pounds per cubic foot for soil density is very light, very bad. So engineering analysis, evaluation of soil properties, consideration of calculation model and input data, settlement analysis and monitoring information, consideration of dome construction, evaluation of the dome materials. That was the engineering analysis. Here's the dome. That's the failure edge, the yellow. And the blue ones are stress values. This is the stress right here. Stress at 50 feet deep. That's where the limits of stresses are. Limits of stresses at 100 foot deep. Limits of stress at 200 foot deep. Notice these CPT8 and R5 are outside the stress level, so they were not impacted. So what you can say is, as it can be seen from the diagrams, the soils at CPU 8, 15, and R5 have not been affected by the construction because they were outside the stress zone. Therefore, it is reasonable to assume that the soil parameters obtained from CPT 18 here represent the original soil conditions. CPT 8 and CPU 15 at boring R5 will be compared to these values of the stuff that we got over here. So when we look at the CPT data, this is CPT 8, the blue one. That's what's kind of like there was no effect. We can see that the CPT that was in here is this CPU 16. That was, that's number 16, which was in here somewhere. I can't tell because it's underneath. Here, CPU 16, which was near the failure. They got strain hardening. The soil got stronger because of strain, but not in the organic layer. But everywhere else, it got a little strength because of the straining. Same with this one here. This is another CP17, CPU18 that shows strength gain with compression and settlement, called strain hardening. Again, this is CPU19. We saw got stronger near the top, stronger below the organic layer. This is CPU20. This is the organic layer. No increase of stress in strength, but in the natural soil above it and below it, it gains strength. Again, these are within the failure area, CP20, CP19. If you look at it, CP18, CP18, 18, 20, these are they gain strength with straining, settlement. If you do classify the soils based on cone penetrometer testing, most of the soil end up as lean clay, and a lot of it shows up at number 2, organic soils and peat. So they went out there and put this heavy structure on top of organic soils and peat. They didn't pay attention to the data. Again, if you look at the data, you got moisture contents as high as 200, density as low as 50 PCF, and in strength values of as much as 0.25 KSF, which gives you very low bearing capacity. This is a picture of the soft organic clays that's there. Soil investigation from CPT and the borings indicate presence of soft organic soil layer from 15 feet to 35 feet. The data from CPT indicates that the strength of organic soil layer did not increase after construction activities due to strain hardening. The initial design of the dome failed to consider the presence of soft organic layer. So initially they went out there and they filled up about 77 metric tons. Then the second time they loaded up, they went to 125 tons per metric tons. This is the model they used. But if you use this model here, you got to have high stresses in the middle and low stresses at the edge, which causes major differential movement. They use the wrong model. If you use this model here, you can see this area here has got 5.2 TSF. That's 10,000 pounds of load at the center and about 4,400 PSF at the edge. So at 125 metric tons of loading, design pressure is about 2.6 TSF for assumption of uniform load, but for actual pressure is 5.2 TSF. Using uniform load conditions in the period of dome design provides higher safety factors than actual load conditions, which is not correct. Using the uniform load conditions in the period of dome design gives less differential movements than actual differential movement that were measured. These are the values of the strength values. You got average shear strength of 0.5 TSF. Using a shear strength of 0.5 TSF, you got an allowable bearing capacity of 2.572 TSF. Your factor of safety at the edge, at the center, is 0.5, at the edge is 1.2. I mean, that's a simple bearing capacity calculation. You don't go out there and put, 5.2 tons TSF of load on soft soils. They did the calculations for Dome 1 settlement after 1 year. They said that the middle settles about 2.7 foot deep settlement, 2.75, and then at the edge 0.8. It said differential movement measured the first loading of 77,000 metric tons was 2 foot, which is 2.5 times greater than the original predicted differential settlement. So the 2 foot measured after 77 metric tons, 77,000 was 2 foot, 2.5 times more. The problem with the soil model was they used both Phi angle and C angle, which makes the model so actually stronger than what it is. And when you calculate bearing capacity, you only use C, you don't use Phi. The Phi is 0. If you run the triaxial test for Phi of 20 degrees and C of 0.7, your actual shear strength that you have to, if effective strength is what, 1.8 KSF, which is significantly higher than what the actual soil strengths are, 1.8 KSF. So as it can be seen, combining the cohesion of 0.7 with 23 degrees cohesion is 1.8 KSF cohesion without frictional angle. This corresponds to a cohesion of model that is 2.57 times greater than actual cohesion at this step. The safety factor using the dome model was 2.56. Combining 0.7 with 23 angles overestimates the bearing capacity. In addition, the results of the cone penetrometer testing indicates the soil strengths from 9 to 21 feet did not increase when loading of the dome, suggesting friction angle in the combination of soil cohesion to compute stability is not reasonable. So here's the conclusion. The assumption of uniform soil conditions is not conservative. Actual loading is 1.5 times greater than assumed. Assumption of a uniform loading resulted in underestimation of differential movement. The actual differential movements were 2.5 times greater than what they're assumed. Combining underrange strengths with friction angle gives you higher overall strength of the soil. The actual safety factor is 2.5 times less than the assumed designed. So when they were building this thing, these dome, they put settlement monitors here. These PK settlement points are for the tunnel, PK, the blue ones. These red ones are for the ring beam. So ring beam sits on top of the soil solution, which is 39 by 12 foot deep. And this DMB1, which is on the ring beam, is settlement monitor, is right next to the tunnel. That's PK12. And here is PK1 and DMB3. DMB3 is settlement monitor on the ring beam. PK1 is settlement monitor on the tunnel. Okay, so if you look at this thing here, settlement monitoring, as they were building it from 0 to day 600, this thing started settling, you know, as they were loading it. And when they start putting the product in there, the iron ore, you can see the whole thing start failing. Okay? And you can see this is DMB3, DMB1, these are the settlements monitoring around the ring beam. These are the ring beam settlements for 600 feet days. Now, if you just go out there from 550 days and on, you can see when they started loading on July 29, 2013, the settlements start dropping. And when they stopped, the ring beam differential movement was 4 inches. Maximum settlement of the ring beam foundation was 9 inches between the ring beam, maximum. So here's the ring beam settlements at the loading of 77,000 metric tons. This is PK12, which is on the tunnel, right next to it. You see tunnel starts sinking, the ring beam followed it. Then all of a sudden, ring beam cracked and the settlements became equal. This is September 23rd, 2017. This is settlements versus days. So DMB1, which is the settlement monitor on the ring beam, had to be settled more than equal to PK12 on the tunnel because they're right next to each other. However, as it can be seen from the diagrams, the settlement at PK12 tunnel is significantly greater than at DMB1. This means that the gap created between the ring beam and the foundation tunnel The gap between the ring beam and tunnel closed gradually by second loading until collapse on September 26, 2013. At this time, the gap closed completely. So, and here's again at 77,000 metric ton loading. Here's the ring beam. Here's the tunnel. They were pretty close, but then all of a sudden, ring beam fails. You can see the failure on September 23rd. In general settlements at DMB1 and ring beam, foundation was equal to the PK12 in the tunnel during the first loading. This reflects that the soil below the foundation dome 1 at this position is relatively stable. The second loading settlements on the 24th, 25th were not found. This was difficult to evaluate the stability at this point. But here these are the settlements of the ring beam on the September 23rd. Here's the failure. You can see that. These are the settlements at 77,000 pounds of metric tons, July 29, July 31st, September 23rd. You can see the settlement at the center of 2.5 feet, at the edge 0.5 with 2 foot of differential movement. Okay, you can see the settlements in here. This is just 125 tons when the second loading. And you can see the settlements are roughly about 2.5 feet and 0.5 with 2 foot of differential movement. The maximum settlement was 2.5 feet. The consolidation settlement was 1.2 feet. Initial elastic settlement was 1.3 feet. The differential was 2 feet. Here are the cracks in the tunnel as this thing was settling. You can see the whole west area when the soil bulged up. The shape of iron ore did not change after the collapse. This means that the lateral pressure on the dome imposed on the dome wall was not significant. It is evident that the failure of the dome structure occurred first in the stacking tube. After the failure of the stacking tube foundation, a huge force was induced to push the tunnel outward toward the west. As a result, ring beam was also shifted towards the west. Finally, moving tunnel and ring beam resulted in heaving of the soil. It's the heaving of the soil here. When they said they compacted soil underneath the floor slabs, underneath the dome, they say they compacted to modified proctor. That's a very strong compaction. That was in the specs. But during the construction, they compacted soil to standard proctor, which is a lot less compaction. So that was one of the other construction defect on this case, poor compaction of the soil underneath the floor slabs. Causation for dome 1 failure. Underestimation of differential settlement in dome design using incorrect strain hardening model. Overestimation of the bearing capacity. They said bearing capacity 2.56. We calculated to be about 0.5. Failed to consider the presence of organic soils. Did not conduct adequate testing of the strength. They hardly tested soil in strength. That was crazy. Bad compaction underneath the floor slabs. They use a standard proctor instead of modified proctor. To back calculate the failure using the new soil data that we got, if you plot the new soil data and calculate bearing capacity using the loading, you get a factor of safety of 0.4 using the new soil data. So, I mean, they really overestimated the bearing capacity here. And here's the whole three-dimensional movement of the soil underneath the dome. Conclusion. The differential movement between the center and edge of the foundation measured to be 2.5 times greater than predicted. The underestimation of the differential settlement in the dome design attributed using incorrect model. Collapse of stacking tube due to excessive differential of settlement resulted in failure of the ring beam. The assumption of uniform loading condition in the design resulted in underestimation of iron ore pile stresses. The actual pile stresses under the foundation was 1.5 times greater than what was assumed. The bearing capacity of the soil was overestimated. They used 2.6. We came up as much as 0.5 inches. The factor of safety of 1.5. Failed to identify and consider presence of organic soils. Back calculation of factor of safety for bearing capacity showed a bearing capacity of 0.41 for short term. Damage model. Okay, how are we going to repair this thing? Well, the end result is you can't repair it. So you got to tear it down, go in there with pile foundation, control modulus columns from Menard, or do compaction grouting. Pile foundations, you go out there depending on the loading on the structure. You drive the piles to about 100 foot deep, and some of them 60 foot deep. A lot of piles, they said it was too expensive. Control modulus columns. These guys go in there and drill basically a specially designed displacement auger installed on a machine equipped with tri-torque, static vertical truss. The soil is displaced outside the column. Then they put grout injected in there. The amount of grout is selected to achieve the design stiffness. So they go in there, drill, and fill this hole with grout. And grout comes up and strings the soil here in the column, called control modulus. That's what it looks like. You have a bunch of them in there.
Controlled modulus columns, CMCs, have been specially designed to improve soils with weak load-bearing capacities and with a high deformation. They enable the implementation of shallow foundation solutions on soils that would otherwise require deep foundations. This technique is based on the optimal distribution of loads between the inclusions and the surrounding soil. The inclusions are installed into the ground on a regular grid pattern using a specialized boring tool until they reach an adequately deep layer and are then filled with pumped grout or concrete. The installed CMCs are covered by a load transfer platform, also called a granular mattress, before constructing the structure's ground-bearing foundations. The diameter of the columns is between 250 and 450 millimeters. The grout or concrete is injected through the hollow core of the boring tool from bottom to top and at low pressure to ensure the continuity of the concreting throughout the process. The columns are installed using special equipment providing a high rotation torque and powerful pull-down, which is capable of moving the soil laterally, thereby increasing its density without generating any spoil. These rigs are fitted with a quality control system which continually records the boring and injection parameters, making this a valuable tool for monitoring work in real time. The method offers 4 advantages: suitable for ground-bearing foundations and significantly reducing settlements, environmentally sustainable solution, optimization of concrete and steel quantities used, quick installation process. As the pioneer of this technique, Menard can now draw on more than 20 years of experience in the installation of this type of solution. The company has already deployed it on more than 2,500 sites worldwide.
So we had the piling that goes to that dense layer of sand that was here. It was 200 foot deep or so. Or you can go with basically with skin friction or using Menard CMC. That was another option. Piling was definitely better. The other option we looked at is compaction grouting. Get that soft organic soils and grout it and put grout under pressure and fill it up and densify it. Compaction grouting is the injecting of the stiff mortar kind of grout under high internal friction into the soil mass and stiffen the area. Compaction grouting improvement displaces the soft soils and densifies the soil. Here's the grout coming out underneath the foundation. Compaction grouting has been used to increase bearing capacity. Compaction grouting is usually started at the bottom and comes to the top. Compaction grouting is very effective, targeting isolated zone depths. However, it's generally difficult to achieve at shallow depths of 8 feet. Here's the device that uses compaction grouting. Compaction grouting. Basically, based on what we're looking at all this stuff, we told them to remove everything and just go with piling. The construction cost was about $95 million. We got a bunch of new webinars coming up. This is kind of our schedule. February 10th, we're going to have guidelines for design and construction of swimming pools. Case histories on the 223 crane failures. March 16th, design and construction of the residential foundations. Make sure you send us your information so that you are on our email address so that you get these webinars notices. If you got good pictures of projects, please send them to me. I use the pictures for the seminars. These seminars and others are on the YouTube Geotech Engineering and Testing channel. Program evaluation. I appreciate it if you guys go in there and fill out the program evaluation. And tell us what you think. If you need to reach me, my email is de@geotecheng.com. Phone number is 713-699-4000. You're going to get 1 hour PDH hour on this thing that was going to be emailed to you. Questions? Ray is asking, what method of repair did the owner use? You know, we were involved in the litigation on this thing here. I think they went in there and settled it. I don't know what the owners did really after that. But if it was my money, I'd go spend the money and do piles. So, you know, let's see. I don't know if the poll. Okay, we'll just send the poll out. Yes. The next question, Gary Board. Where's the questionnaire? Oh, the poll. We just sent out the poll. Okay, and then we don't know what repair techniques. Lauren, very informative. Any other questions? Well, I appreciate everybody's time. You know, if y'all need to reach me or need some help on some geotechnical material testing projects, environmental or forensics, please call me. We're always ready to go in here. Y'all have a great day. We'll see you soon.